Let's do a problem from your lab assignment, section 8.3. Here we have a triangular plate with a base of 4 meters and a height of 6 meters. And it's submerged vertically into the water so that the tip is even with the surface. Express the hydrostatic force against one side of the plate as an integral and then evaluate it. So here's a little bit of background for hydrostatic force and pressure. We're going to do this in SI units in the metric system. And so the pressure is going to be given in newtons per square meter. It's also known as a Pascal, but that's not going to be important because we're going to eventually want the force, and the force will be in newtons. What's going to be needed here is the pressure is equal to the density times the gravity times the depth. So this is going to have a certain pressure and a certain depth. And then the force is going to be the pressure times the area. So we're going to need to compute areas here, and that's where the integral is going to come in. The algorithm is going to be as follows. We're going to find a relationship between the area and the depth. And so the depth is what's changing here, the changing variable. And really what we're going to look at is the width of our surface area, because we're going to have the thickness give us a rectangular region. I know this is a triangle, but we're going to get rectangular regions with a certain thickness, and then the more regions we get, the more it's going to look like a triangle. We're going to find the pressure using the formula, and then we're going to find the force by multiplying the pressure times the area that we had just found. So we found the area in step 1, we found the pressure in step 2. We're going to multiply them, and then this product that we're going to get will have a delta x, the thickness of the strip, and so that's going to make into a Riemann sum, and then we're going to change that Riemann sum into a definite integral and then finally compute it. Alright, let's take a look at this problem. We have similar triangles here we're going to use. What they did was they looked at an arbitrary cut in the middle. It doesn't necessarily have to be in the middle. It could be closer to the top or closer to the bottom. It's an arbitrary cut between the top and the bottom part of the region. But in any case, if we're matching up with similar triangles here, we have w over 4, so that's the width, and then now the height of the top triangle is x sub I, and the height of the whole triangle is 6. And we really want the width of this thing, so we're going to multiply both sides by 4, and we're going to get 4 over 6 times x sub I star, and then to give us the thickness with a delta x. So we have 4 over 6, and I suppose that can reduce to 2/3. So now that we have the area, or the width is the 2/3 times x sub I star, and then the area is that times the height, which is delta x. So now that we have the area, we're going to find the density. The density is just rho times g times d. So we have the density times the gravity times the depth, and this particular strip here has depth x sub I star, so that's x sub I star here. So it's just rho times gravity. Okay, so now that we have that, let's collect the hydrostatic force. The force is going to be the pressure times the area. So we found the pressure Pg x sub I star, or that's rho, it's not P. It's rho times G times x sub I star, and then the area has 2/3 x sub I star times delta x. So that's a second x sub I star and the delta x. So we just need a 2/3 with us, and I think that's good. And so now we're going to create a Riemann sum. This is everything that we want to add up, really. The force, we want to add up all the force. And so we're just going to go from 1 to n. And n goes off to infinity here. We're going to go from 1 to n and add up a bunch of the force on all the strips here. And so that changes into an integral. So the integral is going to go from 0 to whatever the top limit is. Now remember that this goes downward, so the top limit is actually 6. So it's going to go from 0 to 6. And then we're going to put in this quantity over here. Well, almost that quantity. It looks like they took the rho times g out. And so they kept the 2/3 in here. And then we don't have to use x sub I star anymore, because we're going to take the limit as n goes off to infinity, and that's just going to be x values. But it is being squared, so we make sure we square that. The delta x becomes a dx, and that is our integral. So now it's just a matter of computing the integral. We compute the integral, we take the constant 2/3 out, and the antiderivative of x squared is x cubed over 3. We're going to evaluate this from 0 to 6. If we put 0 in, that's going to get 0. And if we put 6 in, we're going to get 6 cubed. 6 times, let's take out our calculator here. 6 times 6 times 6 is 216. So that's 216 times 2. And then we're going to divide by 3 and 3, so divided by 9. And we get 48. Oops. Let's keep this as cubed, and this is 48. So this is a total force in newtons, and so this would be your answer, except they want us to put rho and g. Now, rho, if this is water, we're assuming this is water, the density is 1,000 kilograms per square meter, and then gravity is 9.8. So I think I just need to take that 48 and multiply it by the density, and then multiply it by the gravity. And I get 470,400. That's the total force on the side of that triangular area. Okay, I hope that helps.